Okay, so as I explained previously about the data transformation, so the data transformation, it is a function, okay, to change a value from the original value to a new value. So there are some methods in the data transformation. We call it smoothing. So smoothing means to remove noise from data. And we have attribute or feature construction. When we want to construct a new thing, okay, so we learn in the data reduction strategy. In one of the data reduction strategy, we have the attribute or feature construction. So we can create new attributes constructed from the given one. Okay. This is also one of the data transformation. Aggregation. So we can make summary, or we can create the data cube. Okay, so we call also data transformation. Normalization. So in the normalization, it is scaled to fall within a smaller value or in the specified range. So we will learn those three: minimum, maximum normalization, set score normalization, and normalization by decimal scaling. And we can also learn some concept about the discretization. So it is the concept of hierarchy climbing. Okay. So let's learn one by one. Normalization. We call min max normalization. Min max. So min is minimum, max mean maximum. So we want to normalize the value into a new minimum and new maximum. Okay. So we use this symbol. It is to represent what is the minimum, the new minimum, and what is the new maximum. Usually, we can have like the new minimum is 0 and the new maximum is 1. So this is the common normalization. Let's say if you have huge money, let's say ilok, okay, 100 million won, okay, ilok won. Then the zero, there are a lot of zero, and it is not proper for your analysis, because maybe you want to compare someone's salary is maybe someone's salary is 2 million Korean won, but some rich people, they can get the salary 100 million Korean won. So it's totally different value. In order to fit with the analysis, we can normalize. And the normalization usually between 0 until 1, or yeah, you can determine the value. Maybe 0 until 10, that's also fine. So the formula will be like this one. You can have a new value, and the new value will be based on the what is the value now, and then minus the minimum A divided by maximum A minus minimum A. So this minimum A means the actual value, the minimum from the data. And then the maximum A is the maximum from the data. And then we want to transform to the new maximum and to the new minimum. Let's say I have the income. The income is from 1,000 US dollar to 8,000 US dollar. Okay. So this is the minimum, and this is the maximum. Okay. So I have the minimum and I have the maximum, and I want to normalize this data into 0 and 1. Then if I have a value 6,000 US dollar, what is the new value? What is the normalized value? So we put 6,000. This is the value that we want to convert. minus by 1000, which is the minimum, and then divided by 8000, which is the maximum, minus 1000, which is the minimum. And we want to change it into the new maximum, which is 1. Okay, the new maximum, which is 1, and then the new minimum, which is 0. Okay. And then plus the new minimum. The new minimum is 0. So we get the value here is 0.714. Okay. If I want to change 1000 US dollar with this transformation, what is the value? What is the normalized value? If I have 1000 US dollar, what is the normalized value? Yeah, anybody? We can calculate. Okay, that's correct. Okay, 0, because 1000 minus 1000, it is already 0. Okay, so you don't need to think more because I know that the minimum is 0. So the normalized value will be 0. What is the normalized value of 8000 with this range? Yeah, okay, that's correct. So if 8000, then we will have the normalized value as 1 because it is the maximum. Yeah, 8000 minus 1000, and then 8000 minus 1000. So we have 7000 divided by 7000. Then it is equal to 1. Okay. Then yeah, you can know that if it is the minimum, it will be the 0, and then if it is the maximum, it will be 1. Okay. Thank you. Okay, thank you for your answer. We have another normalization. We call it Z-score normalization. The Z-score normalization, it is from the mean and the standard deviation that you obtain. Okay. You have some data, and then you can calculate the mean. You have some data, you can calculate the standard deviation. So, for example, I have a value. Okay, I have a value 6000, and then I have mu, or the mean is 5000, and then I have the standard deviation. The standard deviation is about 1250. Then what is the new value, or what is the normalized value? Then we can use this formula. Okay. 6000 is the value that I want to change, minus by 5000, which is the mu of the actual value, the mu of the data, divided by the standard deviation of the data. So we can get the value, or the normalized value is 0.8. Okay. So we call this is the normalized value. So if I can show you more details. Okay. Yeah, so this is the more details when you want to use this standardizing the numerical data. Okay. Yeah, we have the Z-score. The Z-score is the value itself minus by the mu divided by the standard deviation. Okay. So X means the row score. Okay. Mean is the mean of population and the standard deviation. And there are some ways to measure this kind of standardizing the numerical data. I think last time, do I explain this one? I forgot. So there's another. If we have the negative, okay, yeah, there might be possibility for the negative. Okay, it means if the value, for example, x is 4,000. Okay. So if the mu is 5,000, of course it is negative. Okay, there might be a possibility of negative. So if it is negative, what happens? Yeah, it depends on your needs. What do you want to analyze? If you do not want to have negative, okay, if it is like 4,000 you minus 5,000, yeah, of course it is negative. Then there is another alternative way. We can use mean absolute deviation. Okay. So in the mean absolute deviation, it means I want to get the mean. Okay. So I want to get the mean, and the standard deviation. Okay. The standard deviation will be using the value from the real value minus by the average, and then we put the absolute. Okay. So if we have this SF, we have the value that we already have the standardized already, the standard based on the standard deviation. Okay. And then we want to calculate with the absolute deviation. Maybe I can show you an example here. Okay. As I remember, we already learned a little bit about this calculation based on the person correlation. Okay, so this I want to show you another example. This is about the mean square error. Let's say I have the data 90, 75, 85, 180. So the mean is 86. Okay. And what about the standard deviation? Okay. So with the standard deviation, we have the 16, 121, 196, 36, and then we can do the square root. Okay. So this summation is 370 divided by 5, which is the sample number, and then we will get the standard deviation is 8.6. So this is the mean, and this is the standard deviation 8.6. If we use the mean absolute deviation, so we do not use the square like this one, but we use the only the absolute value. Okay. So the number will be smaller. Okay. So if you take a look on this one, if the number is smaller, you have this MAT like this one. Then okay, you have this mean and you have this MAT. You can convert. How you convert the value? The first value is 90. Okay. The first value is 90. Then I want to convert this 90 to the new value or the new Z with the Z score minus by the average divided by the standard deviation. So we get the score Z value or the normalized value for Z1 is 0.46. In the Z2, yeah, we have minus. Okay, so there's a minus. But of course, you can see here, this value is very small. This value is a little bit larger. Okay, because we have the value of the standard deviation using the MAD. We use this mean absolute deviation instead of the mean square error. Okay, so this is the result from the mean square error, and this is the result from the mean absolute deviation. Okay, so this is the standard deviation. This is the MAD. Okay, 7.8, and then this is the mean 8.86. So we can get the new value after the normalization. This is the normalization based on MSE, and this is the normalization after we have the mean absolute deviation. Okay. The other kind of normalization, it calls by normalization by decimal scaling. So the normalization by decimal scaling, we have like a new v, okay, v prime will be equal to the v, which is the value divided by 10 power of j. What is j? J is the smallest integer such that the maximum of v, okay, the maximum of the new value will be less than 1. Okay, what does it mean? Okay, maybe it's difficult to understand like this one. So let's see what with example. Okay, so we have this formula. Okay, we have this formula. We have the v prime equals to v divided by 10 power of j. We have like this data. Okay, we have minus 10, 201, 301, minus 401, 501, 601, and 701. Okay. What is the maximum here? The maximum with absolute. Okay, so we will do the absolute from the maximum value, and then we want to find which value is less than 1. So to normalize the above data, first we will find the maximum absolute value. It's easier, okay, because if we make this absolute, okay, if we make, I think it's the same like this one. Okay, we can make absolute this one, so we can just find the maximum absolute value, which is 701, and then after we found the 701, iterate j until it satisfies the condition. The condition is the value should be less than 1. Now let j equals to, maybe, okay, before j equals to 2, let j equals to 1. What happens if j equals to 1? So 701 divided by 10. 701 divided by 10, it is 70.1. 70.1, is it less than 1? No. Okay, so it means j equals to 1 is not the answer. So let j equals to 2. What is j equals to 2? So we have 701. We want to divide it by 10 power of j. J equals to 2, then power of 2. So we will have 701 divided by 100. So 701 divided by 100, it equals to 7.01. 7.01, is it less than 1? No. Okay, then we will move to the next one. Let j equals to 3. Okay, so j equals to 3 means, oh sorry, I think it's overlapping. Okay, then j equals to 3. Okay, when we want to find this, okay, when we want to divide 701 with 10 power of 3, okay, so 701 divided by 1000, so we can get the value 0.701. Is it less than 1? Okay, yes. So we will choose j equal to 3, because the condition should be the maximum of the value, it should be less then 1. After we have this, then we choose j equals to 3 and we divide all the data with 1000. Why? Because we have j equals to 3. So 10 exponent 3, it means 1000. So the new value will be the normalized data for every of these data will be like this one. Okay, so this is the normalized data after using this normalized with decimal scaling. Okay, hopefully you understand. Yeah. We can deal with the discretization. What is discretization? There are 3 kind of attributes. Okay. Of course, you ask me why 3? Because we know that those 2 are belong to categorical data. You still remember? Okay, those 2 are the categorical. Nominal, it means we have no sequence, no order. Ordinal, we have the order. Okay, this is unordered. So color, profession, military, academic rank is the ordinal. Numeric, okay, numeric, is integer or the real numbers. So if we deal with the discretization, it means we want to divide the range of continuous attributes into interval. Okay, so if we have a continuous attribute from 0 until 100, okay, so we can make discretize 1, 2, 3, 4. Okay, then we select the limit. Okay, maybe this is until 25. Okay, this is until 50, and this is until 75. Yeah, for example. Okay. So how we can do this discretization? So there are some ways. Okay. We can have the interval labels that can be used to replace the actual data values. So the most common interval labels is from 8. Okay, maybe I don't know, from 0 until 5. Yeah, we can say children. I don't know, 5 or maybe not children, baby. Okay, yeah, from 4 until maybe 12, we call it children. From 13 until maybe 18, we call it teenager. Okay. From 19 until 30, we call it youth. Okay. Maybe from 31 until 60, we call it adult. Yeah. So something like this one, we put the label. What is the label? Yeah, this is the label: baby, children, teenager, youth, adult. So if your age is 2, then I can put the label directly baby. If your age is 15, okay, I can put the label directly is teenager. Okay, so that's the meaning by the interval labels. We can reduce the data size by discretization. Yeah, using this kind of discretization, we can reduce the data. And there are some ways like supervised versus unsupervised. Yeah, we will learn about this one. So there are some methods for discretization using the supervised and unsupervised. Or we can make the split, which is top down, or merge, which is bottom up. Okay, so the idea of split and merge is similar with the way that we learn about the aggregation. Okay. So when we have like the second, okay, we want to make it as daily. So yeah, we want to aggregate. So we call it, this is bottom up. From the bottom, we want to make the like the summary on daily. Or if we have the top down, let's say if I have the electronic products, then yeah, I want to split again. Maybe this is computer, smartphone, and for example webcam, and etc. Okay, so it means you can split into another detailed products. Discretization can be performed recursively. Okay, and you need to prepare further analysis, like for example the classification. So we will learn those things later. There are some ways for the discretization. We will learn the pinning. Okay, pinning means, yeah, I have the data like this one, and then I want to pin. So I want to make it as pin like this one. So this is the first pin, this is the second pin, this is the third pin, fourth pin, fifth pin, and sixth pin. Okay. We have top-down split and unsupervised for this kind of pinning. And we can use the histogram analysis. So the histogram analysis here is using the pinning actually. We can use clustering analysis. So we can group. If they are in the same group, maybe it's easy to understand if you are in the same batch. You are the year of 2018, or the year in 2017, or you are the year in 2019. So you can be in the group because you are similar. You have the similar characteristics on the year. Decision tree analysis. Yeah, we can use some methods later in the supervised and the top-down split. Or you can use the correlation analysis, the chi-square analysis. The chi-square analysis means you can see the correlation. If the data are correlated, then yeah, you can make the discretized value. Pinning is a simple discretization. There are two types of pinning. The first is equal width, and the other is equal depth. The equal width or equal distance partitioning, it divides the range into an interval of equal size or uniform grid. So if I have this data, so it should be equal on the width. Okay? It should be equal on the width. So the data will be equal interval or equal distance. In order to do this equal width, we have the A and B, which is the lowest and the highest value. So let's say this is the A, the lowest, and B is the highest. So the width of interval will be W is equal to B minus A divided by N. Okay. It is the most straightforward, but outliers may dominate presentation. In this case, Q data is not handled well. Okay. Therefore, there is another approach. We call it equal depth or equal frequency partitioning. We divide the range into n intervals, so it's containing approximately same number of samples. So if I have like this one, okay, I have this data, and I need to check how many sample of the data. If we have like this one, yeah, like this one. If I have 9 data, then I can make the discretization. Let's say I want to make 3 intervals, so I can just split this one, and then I split this one, and then I split this one. So there will be, these are 3, and then this is also 3, and this one also 3. but the width is different. This is very small, this a little bit wider, and this is very wide. Yeah, we call this is equal depth or equal frequency. It is good data scaling, and yeah, managing categorical attributes can be tricky. Okay, so this is just a very simple discretization. So in the real data, yeah, you may have some issues with this kind of discretization. So for example, I have this data. Okay, so usually when you are doing the binning, you need to sort the data. Okay. So this is the sorted data. 4, 8, 9, 15, 21, 21, 24, 25, 26, 28, 29, and 34. If you want to partition the data into equal frequency or equidepth. What is equidepth? So we want to put the same frequency. The same frequency means, yeah, the same number of elements. So in the bin 1, there will be 4 elements. In the bin 2, there will be 4 elements. And in the bin 3, there will be 4 elements, because we know that there are 12 elements in the row. Okay. If we are doing the smoothing, okay, so this is partition. So the transformation, okay, we call it this is, if you take a look on the previous chapter, this is the transformation. Okay, so one of the transformation is using the smoothing. How can we smooth this data based on the bin? So first is the very simple smoothing by means, or the bin means. Here you can see what is the mean. 4 plus 8 plus 9 plus 15 divided by 4. Okay, so we can just get the nearest integer. So I do not want to make the complicated one, so we can just use the 9 as the mean. So every number will be smoothed or will be transformed 9, 9, 9, 9. Okay. What about this? Yeah, you can calculate the means and 23, 23, 23, 23. So we call this is the smoothing. And this is for the last bin. How about if we use bin boundaries? In the bin boundaries, we want to smooth the value based on the minimum or the maximum. Minimum or maximum. It depends on the number which is closer to the minimum or to the maximum. So let's see. 4. Of course, we know that 4 is closer to the minimum. So we put 4. What about 8? 8 is closer to minimum or maximum. We know that it is closer to minimum. Then we just put the minimum. What about 9? Is it closer to minimum or maximum? We know, yeah. If we go to minimum, the gap is 5. If we go to maximum, the gap is 6. So it is closer to minimum. Then we use 4 for the smoothing. 15, yeah, of course, it is the maximum. What about the other? Okay, let's see the bin number 2. In the bin number 2, 21, 21, yeah, because those numbers are the minimum, then we can just put 21, 21. What about 24? Oh, 24 nearby the maximum. So we use 25 for smoothing. And so on. So we have the bin number 3, like this one. Okay, so this is the smoothing by pin boundaries. What is the equi-width? In the previous slide, I told you that we need to determine the W. What is the W? We have the A and P. So the A is the minimum value and P is the maximum value. So the minimum is 4 and the maximum is 34. And I want to make 3 different pins. So I have the 34 minus 4 divided by 3. Oh, let me just change the color. So I have this 34 minus 4 divided by 3, and we have W equals to 10, or the width equals to 10. In this case, I can make the range 4 until 13, 14 until 23, and then 24 until 34. So every number in between 4 until 13, it will be in the pin number 1. So 4, 8, 9 will be in the pin number 1. 14 until 23, it will be in the pin number 2. 24 until 34, it will be in the pin number 3. So this is the meaning by equi-width. And you can see here, there are 3 numbers. There are 3 numbers, and we have 6 numbers here. So the frequency are not same. Different with this one, we call this is equal frequency. So they have the same frequency. Okay. If you want to compare the binning and the clustering, when we have the binning, yeah, we have this. This is the result of binning. This is the equal frequency, and this is the result of k-means clustering. As a matter of fact, the result of clustering is better. Okay, the result of clustering is better. So we will learn more later about the clustering. How can we do clustering to discretize? That's also one of the possible way for discretization. Another way for discretization is using classification. Okay. So in the classification, there's one method named decision tree analysis. Okay. In the decision tree analysis, let's say I have some supervised. Supervised means I know the data, I know the label, I know the content of the data. So if I have this data, let's say it is about the cancer or benign. So, you know, in the medical, we have the benign tumor and the malignant tumor. So there is a data set. It is very famous for this one. You can determine based on the size, based on the color, or based on the specification, whether it is a benign tumor, which is not dangerous, or the malignant tumor. The malignant tumor is a dangerous tumor. Then based on the data, yeah, we can see whether it is cancerous or not. So this is one of the discretization by classification. It is usually top down, and then it requires recursive. So we will discuss later the details. You can use correlation analysis. Okay. The chi-square based discretization. It is also supervised. You need to use the class information, as I mentioned before with the rapid minor. Before we use the supervised or the chi-square, we need to determine the class. So at the time we determine the class, what is the class of the iris? Yeah, we determine where is the setosa, where is the virginica, where is the versicolor. So after we have this class, we can measure the chi-square. We call this is the bottom up merge. Yeah, so we can find the best neighboring intervals. So if they are very similar, then we can merge. Merge perform recursively until a predefined stopping condition. When we have the discretization or the transformation, we can use also the concept hierarchy. So the concept of hierarchy means we want to organize the concept. Concept means the attribute values, okay, hierarchically, and is usually associated with each dimension in the data warehouse. So I already teach you about the aggregation. If you still remember, in the aggregation, we usually, we have the component of time, location, and items. So those are the commons. Okay, but yeah, we can also have the other kind of aggregation. And the concept here, what I want to explain to you is about the drilling and rolling. So we will learn a little bit about data warehouse. What is the data warehouse? If we are doing the rolling or drilling, means it is the same with this kind of aggregation, whether we are going to top down or bottom up. Okay. Concept hierarchy formation, it is recursively reduce the data by collecting and replacing the low level concept such as numerical value power h by higher level concept such as youth, adult, senior. So in this case, yeah, we call this is bottom up. If it is bottom up, we want to roll up. Okay. Roll up, or yeah, this is rolling. So we roll the data into the new hierarchical concept. For example, if it is the New York, Chicago, Arizona, we want to roll into USA. Okay. If drill down or drilling means we want to make it a detail. So if it is Q1, so we want to make it January, February, March, and April. So it is drill down. Okay. Drilling, roll up, rolling. So they are using the same keyword. Okay. Drilling is drill down, rolling is the roll up. So the concept hierarchy generation with the nominal data, if you have street, city, state, country. So this is the sequence. Okay. And if you are using the specification of hierarchy of set of value, we can use like this Urbana, Campaign, Chicago. So it is in the Illinois state. So it is the higher value. Specification of not a partial set of attributes. Okay. Only street and city, not others. So you can use this one also for the concept hierarchy. And we can make the automatic generation of hierarchies of with the attribute levels. So a set of attributes like street, city, state, country. So it is in one set. That's also one of the possibility for doing the concept hierarchy. Okay, I guess it's the time for us to stop. I will continue again this on the next session. So please prepare your quiz.